Welcome to solverfy.
This is the answer to Chapter 20, problem number 7 from the Smith Organic Chemistry textbook. And in this problem, we're asked to draw the products formed when this molecule that I've drawn at the top of the screen here is treated with each reagent. And we're given 6 sets of reagents. And so these are all going to be reductions, basically. And so we're going to look at metal hydride reductions versus hydrogen gas and palladium on carbon, and some things, some differences between those types of reagents. So for A, we're treating this molecule with lithium aluminum hydride followed by water. And so that is going to reduce our carbonyl to an alcohol. And it's going to leave the double bond on the other end of the molecule intact. So that's going to be our product for A. So for B, we're using sodium borohydride and methanol. And again, we're going to get a reduction of our ketone while leaving the double bond intact. And although this doesn't say only one equivalent, we are asked later to do the same thing with excess sodium borohydride. So I assume that they meant only one equivalent here. Okay. So that's B. So then looking at C, we're going to use hydrogen gas and palladium on carbon, and only one equivalent of hydrogen gas. And so what's actually going to happen here is that the double bond, the carbon-carbon double bond, is going to be more susceptible than the carbon-oxygen double bond to hydrogenation here. And so we're going to lose the double bond, but the carbonyl will remain intact. So then in D, we're asked to do the same thing, but this time we have excess hydrogen gas. And so since we have excess, first the double bond will be reduced, but then because we have such an excess of hydrogen gas, we will see reduction of the carbonyl as well. And so we get the alcohol, just, 2-hexanol here. Okay. And so then looking at E, like I said, E is a lot like B, except we're using excess sodium borohydride this time. But sodium borohydride is not an aggressive enough reagent to reduce a carbon-carbon double bond. So that alkene is going to still be intact even when we use excess sodium borohydride. We'll still just see reduction at the carbonyl. And then lastly, for F, we're using sodium borodeuteride. And so this is 4 deuteriums instead of the 4 hydrogens on the boron and sodium borohydride. And so this is going to, do the same thing that sodium borohydride would do. So we'll get reduction of our ketone to an alcohol. But the point of this part of this problem is to show that the deuterium, so the deuterium from the sodium borodeuteride actually gets delivered to the carbonyl carbon, and the hydrogen that ends up on the alcohol that we form comes from the methanol solution that this reaction is occurring in. So we're not going to get, the deuteroxide. We'll get a deuterium bound to the carbon that was the carbonyl carbon in the starting material. And we'll still have a hydrogen on our product alcohol. Okay, and so that's the answer to this problem. The only way to really solve it is to just know what these reagents do and know what the differences are between these reagents. And then for F, you do need to know the mechanism by which sodium borohydride reduces a carbonyl. And that's the answer to Chapter 20, problem number 7.